Worksheet problem 18.4 asks us to rank the following compounds in order of lowest to highest melting point, denoting the compound with the lowest melting point as 1. To treat this a little bit similarly to 18.2, I want to orient ourselves when we're talking about melting point and how this relates to intermolecular forces. So the melting point is when we go from being a solid to a liquid. That means that we're going from something that has a very organized, rigidly packed state to something that is less rigidly packed and a little bit more free flowing. It has a little bit more energy in there. So in order to do this, we have to add energy. Any solid molecules that we have pushed really closely together, we have to push these molecules further apart from each other. To relate this to intermolecular forces, this means we have to fight against intermolecular forces because intermolecular forces try to hold things together. That tells us that the stronger intermolecular forces will have the higher melting points. Just to rank our intermolecular forces to get us started, we typically focus only on 3. So we'll say that hydrogen bonding is generally the strongest intermolecular force, followed by dipole-dipole interactions. And then our weakest intermolecular force is London dispersion forces. But it will also be relevant to note that there is one force that is stronger than hydrogen bonding, and that is the strength of ionic bonds. Okay, so let's start with CH3OCH3. We know that oxygen is more electronegative than carbon, so there will be electron density being pulled into the central oxygen and away from these carbons on the side, giving a net dipole moment to this molecule. Having a net dipole moment tells us that this molecule is polar. So now we have to ask ourselves, does it have dipole-dipole interactions only? Or are we looking at something stronger? Are we looking at H bonding? So we have to make that decision. And we can do that by seeing if there are any HFON bonds. Now we do see hydrogens here, but they're bound to a carbon. An HC bond is not strong enough for hydrogen bonding. And as a result, what we see here is only dipole-dipole interactions. Next, we're looking at KCl. If we think back to the first unit of the semester, we know that anything that has a metal bound to a nonmetal is an ionic bond. So this is not covalent. We can't draw a Lewis structure of this. What we know instead is that K plus forms a bond with Cl minus, and so the force at play here is just ionic bonding. Next, we're looking at CH3, CH2, CH3. We know there's a slight electronegativity difference between carbon and hydrogen, so if we wanted to, we could draw the bond dipoles all around, but it is uniform throughout. This ends up being overall nonpolar. We can typically call things that are just combinations of carbon and hydrogen nonpolar molecules. As a result, the only intermolecular force we see in nonpolar molecules are London dispersion forces. Lastly, we're looking at CH3CH2 NH2. So we know that nitrogen is more electronegative than carbon. We know that nitrogen is way more electronegative than hydrogen. What we see overall is that these hydrogens have this partially positive charge, and this nitrogen is partially negative. So this is a polar molecule. And now we have to ask ourselves the question of whether we will only have dipole-dipole interactions, or if we will have hydrogen bonding. Do we have any H bonds? And we see here that we do. So we have a nitrogen bound to a hydrogen here, and a nitrogen bound to a hydrogen here. We see in this species that the strongest intermolecular force is H bonding. Reminding ourselves the relative strengths of intermolecular forces. Ionic bonds are the strongest, followed by hydrogen bonding, then dipole-dipole interactions, and lastly, London dispersion forces. We had said previously that if something has more intermolecular forces, then it will have a higher melting point, and the least intermolecular forces will have the lowest melting point. We want to start with the lowest melting point as 1, and therefore CH3, CH2, CH3 should be our number 1. Next we have CH3O, CH3. Next we have CH3, CH2, NH2, and lastly KCl. So this is the ranking we were able to come up with just by determining what the primary intermolecular force was in each of these compounds.